next example. Let the number of offspring of a given species be a random variable having probability mass function p of x for x equal to 0, 1, 2 and so on, with mean mu and variance sigma square. A population begins with a single parent who produces a random number, say capital N, of progeny, each of which independently produces offspring according to p of x, that is a probability mass function. To form a second generation, find the mean and variance of number of descendants in the second generation. So, let me read out the question again. Let the number of offspring of a given species be a random variable having a probability mass function p of x for x is equal to 0, 1, 2 and so on, with the mean mu and the variance sigma square. A population begins with a single parent who produces a random number, say capital N of progeny, each of which independently produces offspring according to p of x to form a second generation. Find the mean and variance of number of descendants in the second generation. Let capital X is psi 1 plus psi 2 plus psi suffix capital N, where psi I is the number of progeny of the ith offspring of the original parent. Given the p of x is nothing but the probability mass function for the random variable psi i's, and also the expectation of psi i's that is equal to mu, and variance of psi i's that is equal to sigma square. Psi i's are IID random variables. Our interest is to find out what is the expectation of capital X, where capital X is psi 1 plus psi 2 plus and so on till psi suffix n. Here n is also a random variable, that is important. Therefore, this expectation can be computed as n is equal to 0 to infinity the conditional expectation of x given capital N takes a value small n multiplied by the probability mass function of capital N, that is same as summation n is equal to 0 to infinity, that is same as expectation of psi 1 plus psi 2 and so on plus psi suffix small n given capital N takes a value small n multiplied by the probability of n takes a value small n. That is same as you know that the expectation of psi i's are mu. Therefore, this becomes mu can be taken out, then summation n is equal to 0 to infinity n times the probability of capital N takes a value small. That is same as mu and the expectation of the random variable capital N, that is also mu. Therefore, it is mu into mu, that is equal to mu square. Now, we can compute the variance of x the same way, that is expectation of x minus mu square, because the random variable expectation is mu square, the whole square. Further, this can be simplified by expectation of x minus n times mu plus n times mu minus mu square the whole square. One can expand, therefore, you will get it is expectation of x minus n times mu the whole square plus expectation of mu square multiplied by n minus mu the whole square, and the third term becomes 2 times expectation of mu multiplied by x minus n mu into n minus mu by taking mu outside. Now, you can evaluate the first quantity, that is expectation of x minus n mu whole square using the conditional expectation by making summation n is equal to 0 to infinity expectation of x minus n mu whole square given n takes a value small n multiplied by the probability of n takes a value small n. If you substitute the way you have done the expectation and so on, finally you will get the answer, that is sigma square summation n is equal to 1 to infinity n times probability of n is equal to n. That is same as the summation n times p n is same as the mean, that is mu. Therefore, this becomes mu times sigma square. Even though I have skipped 1 or 2 steps, one can get a sigma square summation n times p n, that is same as mu. Therefore, it is mu sigma square. Similarly, you can work out the second that expectation, that is expectation of mu square multiplied by n minus mu whole square. That is same as mu square is constant, the expectation of n minus mu whole square, that is nothing but variance of the random variable n, and the variance of a random variable n is sigma square. Therefore, it is mu square sigma square. Now, we have to evaluate the third expectation, that is expectation of mu times x minus n mu multiplied by n minus mu. Here also one can use the conditional expectation, that is mu times summation n is equal to 0 to infinity expectation of x minus n mu multiplied by n minus mu condition n takes a value small n multiplied by probability of n takes a value n. So, if you simplify, you will get mu times summation n is equal to 0 to infinity n minus mu expectation of x minus n mu given n takes a value small n multiplied by probability of n takes a value small n, that is same as 0, because expectation of x minus n mu given n takes a value small n, that is nothing but expectation of psi 1, psi 2 and so on plus psi n minus n mu, that expectation quantity is going to be 0, because the expectation of psi a's are going to be mu, and this is expectation of psi 1 plus psi 2 and so on plus psi n minus n times mu. Therefore, that becomes 0. Hence, the variance of x, substitute all these 3 variance results, all these expectation results in the above this expression. Therefore, you will get variance of x is going to be mu times sigma square plus mu square sigma square, and third term is going to be 0. Therefore, you will get sigma square mu multiplied by 1 plus mu. This problem is useful in branching processes. Therefore, I discussed in this lecture. Even though there are many more problems of a similar kind, we have chosen a few problems for the illustrative purpose, and we are going to come across similar problems in the course also. Therefore, I have chosen some 5 problems to discuss as a illustrative example. Here is the reference for this lecture.